Good morning, afternoon, and evening, everybody. Welcome to the 56th episode of HYSKY Monthly. I'm your host, Danielle McLean. Today's August 19th, 2024. Most of you know me, but if you don't, I am Danielle McLean, founder and CEO of HYSKY Society. So what is HYSKY Society? HYSKY Society is a 501c3, and our mission is building community to advance clean hydrogen science. Our vision is that we're expert scientists providing fun, sustainable science education to communities. Our objectives are workforce development to equip future professionals with hydrogen skills, community engagement, build positive community relationships, education, provide industry-leading courses and webinars like this, advocacy and awareness to advocate for your hydrogen solutions. You can download our company brochure at hysky.org, HYSKY. And of course, this is HYSKY Monthly. One of the areas we're interested very much is aviation, hydrogen aviation. So real quickly, let's promote this post on LinkedIn. Well, I guess the link doesn't want to work. I don't know why. Odd. I'll provide it in a minute. But when I give you the link, you can just click it and then repost it on LinkedIn. I have no idea why it's not working. That's weird. Firstly, thanks to everybody for your donations to HYSKY. We are based in Houston, Texas, and we were hit pretty hard by Hurricane Beryl. So thank you so much for those of you that donated. Some of the people that donated were Jennifer McLaughlin, Michael Cardinell, Clint Harper, Paul Sarahan, Trish Mackery, Michael Lewison, Peter Connors, Shola Iawali, and so many more. Thank you all so much for donating. Mike Hirschberg, I think, is on this call. Joe Sullivan. I'm not going to read all of the calls, but we truly appreciate it. It helped us bounce back. Also, special thanks to some of our sponsors. HYSKY Aircraft is sponsoring this month's HYSKY Monthly. And if you don't know about HYSKY Aircraft Corporation, you should definitely check them out. They've been around for 80 years, and they're a pioneer in the design of flight testing experimental rotorcraft and unmanned air vehicles, UAVs. So if you want to visit, if you want to learn more about partnering with HYSKY to develop the future of vertical flight, you can look at hysky.com. They're also developing the PA-890, and it's the world's first zero carbon emission hydrogen helicopter. The first, but not the last. It's also sponsored by Vertical Flight Society. Vertical Flight Society is the professional society dedicated to advancing vertical flight and electric flight technology. VFS held the first electric VTOL symposium in 2015 and just held the world's largest eVTOL event in January, including a hydrogen session with HYSKY, HYSKY, and HYSKY. If you're interested in Vertical Flight Society, if you're interested in vertical flight, consider joining VFS today. You can join by visiting vtol.org/ ignore the slash. That was for an old comment. Just vtol.org. Oops, wrong button. Sorry. We're also sponsored by Therm & Co. Therm & Co. provides excellent project management for small to medium-sized organizations. HYSKY uses Therm & Co. for our project management. I see a little typo there. Ever wonder why HYSKY is able to do so much with such a small team? Therm & Co. is why. If you need help with project management, contact Angela at thermandco.com or visit thermandco.com. Also, last but not least, we're sponsored by SoCalGas. SoCalGas is leading the way with innovative hydrogen projects. These include the Angeles Link, which aims to create the largest green hydrogen infrastructure in the nation, and hydrogen blending initiatives that integrate hydrogen into natural gas systems to reduce emissions and improve air quality. Learn more by visiting SoCalGas's website. All of these, as I mentioned, this is our 56th episode. All of these are free on YouTube. You can visit them by, I don't know why these links aren't working. I'll post them later, but you can watch all of these. They're on our website, but they're also on our YouTube. So consider subscribing to our YouTube. All 56 episodes of HYSKY Monthly are on YouTube. It's the largest collection of hydrogen aviation material in existence. It's 100% free. So go there, subscribe. And it helps us keep our material free by you subscribing. If you're looking to market your organization to audiences like this, consider sponsoring HYSKY Monthly. You just saw a word from our sponsors. Sponsorships start at $1,200, and you get a logo on a presentation on a YouTube video. It helps HYSKY keep our content free, and you can sponsor by, please turn your cameras off. Please turn your cameras off. Rishabh, can you make sure people have their cameras off? You can sponsor or learn more about sponsoring by scanning this QR code here. Quick update on our upcoming events. Flying High is just 2 weeks away. It's the world's largest hydrogen aviation event in Las Vegas. Many of you are speaking at Flying High. Many of you are attending Flying High. It's only 2 weeks away. I can't believe it. And I will just quickly show you the program for Flying High. If you haven't already gotten your tickets, I highly encourage you to get them. Day 1, that's September 3rd. That's a Tuesday, September 3rd, 2024, is the hydrogen aviation course. And then the Flying High conference is day 2 and 3, September 4th and 5th. So this is the Flying High, or this is the hydrogen aviation course taught by Rishabh and I. It's 895 add-on. It's 8 hours of everything you wanted to know condensed into 8 hours that'll prepare you for the Flying High conference. So whether you're an expert in aviation or you're an expert in hydrogen, looking to get into aviation, or you're an expert in aviation looking to get into hydrogen, this course is going to give you everything that you need to absorb everything from the following 2 days of the conference. I highly encourage you to take this course. It's a great, really kind of just get you up and running with hydrogen aviation. And then here are the speakers for the conference. I'm not going to name all of the names, that would take forever, but just kind of take it in. And you can also download this program by going to our website. It's at Caesars Forum. And I will give you that link. I can at least do that. So to get the program, just go to this link, and then you will click right here, download program. Easy enough. There we go. Hope to see you in Las Vegas. It's going to be a lot of fun. So then coming up October 8th through November 7th, HYSKY's partnered with AIAA to offer our Advanced Hydrogen Technologies and Design course. That is going to be a game changer. I recommend you also take that course. So you can sign up. I don't have the link. Maybe Rishabh, you could grab that link for the AIAA course. It seems when I converted this to a PDF, it got rid of all my links. We're really excited about this course. This is a 5-week course, 20 hours. So it'll be much more technical than the one that we do in Las Vegas. The one in Las Vegas is high level to get you prepared for the conference. The one that's online with AIAA is technical. It's going to get you into the design space of hydrogen aviation. So really for engineers, students, things like that. You don't have to be an engineer to take the one in Las Vegas, though. And with that, I will pass it over to our amazing co-founder, Rishabh, also our COO. Rishabh, I will leave it to you.
Hey, so hi, this is Rishabh. So let's turn our cameras on. Now it's time to turn the cameras on, and we do our usual.
We're doing our group photo.
Yeah, it's group photo time. We missed you guys. I was looking for photos from last time. Then we remembered that we had to cancel that webinar due to the hurricane. Thank you everyone for putting your donations in. It really helped. It really helped us. We're really glad that you're back and that we have so many people joining us again. So a very high turnout this time as well. We have more people joining in.
Cameras on, do group photo, y'all. I'm telling you, these are historic photos. They go into our annual report. They go on LinkedIn. And when everybody's flying with hydrogen, we can say like, hey, we were there in the very beginning. So we love doing these photos. So we'll give you a sec to turn on your photos. We don't care if you're working from home and you're in your PJs. We don't judge. We just want to see your smiling faces. We do request that you do at least have PJs on though.
Well, this is like the time in Zoom. I remember that one episode where there was a reporter and he was
Yep.
wearing a jacket, but he had only his shorts on. So
Yeah, at least be sitting down if you're doing that. All right,
all
we'll
right,
give
thank you so much.
a couple more minutes. Turn your photos on. Just a couple more people. I'd want to see my full screen, my whole screen filled with photos or your faces. Okay, we're gonna say cheese. Keep
All right,
smiling.
cheese,
We'll do a
everyone.
few.
All right, that should be that. And let's go back, Danielle.
Yep. Thank you all
So
so much.
thank you so much. So joining us today is the incredible Matt Moran. He's a great friend of HYSKY Society, and today he's going to give a talk on liquid hydrogen lessons that he had from his heydays back in NASA. So Matt Moran is the managing member at Moran Innovation LLC. He was a previous manager at Isotherm Energy, and he's been developing power and propulsion systems for more than 40 years. He's been doing breakthrough liquid, slush, and gaseous hydrogen systems since the mid 1980s. That's amazing. Matt was also the sector manager, manager for energy and materials in his last position at NASA, where he worked for 31 years. He's been a co-founder in 7 technology startups. He's provided R&D and engineering support to so many organizations. He has 3 patents, 50 publications, including Cryogenic Fluid Management series. He leads the monthly LH2 ERA webinar. So subscribe to Matt's channel as well. He would give the information and the link out soon. Matt's company, Moran Innovation LLC, develops technologies and systems for customers in the energy, transportation, aerospace, and defense industry sectors. He uses an adaptive systems approach for breakthrough innovation that accelerates systems deployment and product launch. Recent contracts have included NASA and commercial lunar landing systems development, big things, venture-backed hydrogen systems for aircraft and vehicles, propulsion system trade studies for spacecraft and rocket engines, hydrogen-based microgrid and fueling system architectures, and lastly, but not the least, technology transfer and commercialization consulting. Matt is a great guy, and we really welcome you, Matt, and up to you.
Thank you for the introduction, Rishav, and I'm sorry that you had to read through that whole thing. I should have given you a shorter version. I am going to share slides now. It says host disabled attendee screen sharing. So maybe if you can give me that access.
Try now, Matt.
Okay. Still getting the same.
Try one more. Sorry, it should be working.
Oh, there it goes.
Okay, sorry about that.
No problem. Window. Let me make sure I get this and it's visible, everybody. Is that showing up for everyone?
Yep.
Okay. Thank you for inviting me to chat with this group. And good morning, good afternoon, good evening, depending on where you're tuning in from, I guess. Appreciate your attendance, and I'm going to try and leave as much time at the end as possible for live Q&A. I think that's always interesting to kind of see where people are trying to tackle in this area and where their interests are. So, but let me jump right into it then in the time we have, where I'll just present some very high level upfront things, starting with the types of hydrogen storage. Now, I don't include in here liquid organic hydrogen carriers are often called, or other chemical formulations where hydrogen is embedded in them, such as ammonia. So these are just pure liquid hydrogen storage methodologies, which just gets complex enough. But if you go across the top, these are the options available. Underground storage is great for very large amounts of storage, for seasonal or grid type backup. Material-based, sometimes called solid state, has been around for quite a while. The conventional method is metal hydrides, but there's more recent research being done in aerogels and other formulations of matrix materials, which have nano type size volumes where adsorption or absorption of the hydrogen can be attained. Compressed gas is by far the most common in use in the commercial sector. So probably a lot of you are familiar with that. Up to 700 bar containers are now available. I'm going to talk about in this talk that fourth column over, cryogenic liquid storage, which is where most of the experience, not just at NASA, but in the space industry worldwide, globally, has been concentrated over the last 60 years. I will mention cryo compressed only because there's a lot of good stuff going on there as well, and it does have application to the mobile sector in general and potentially to aviation. And that's the last column, but I won't dig into that with this particular presentation, but I wanted to make you aware of it. If you are interested in this, this is an area that Department of Energy, the U.S. Department of Energy, has done a lot of work over at least a decade or two, probably close to 2 decades. And now Daimler has a fueling system based on it, and a startup called Vern is working in this area as well, just 2 examples. So focusing right now on cryogenic liquid hydrogen, some of the characteristics of it compared to these other storage methods. Low pressure, which is goodness in terms of the structural. You don't need a lot of structure, or as much structure, I should say, as a high pressure system. So lower mass. However, you've got to keep it maintained at a very cold temperature, minus 253 degrees C, roughly, or about 20 degrees Kelvin in absolute temperature. The energy primarily going into storing it in this mode is the liquefaction required. Roughly about 30% of the lower heating value of hydrogen to liquefy it by conventional methods. Now that number is dropping as new technologies are brought on, and there are other cryo cooler and smaller methods that I'll just touch on briefly in this presentation. Now you can transport it, which has been done for a long time by over-the-road trucks. Or you can produce it on site and use it on site, which is what a lot of the newer concepts are looking at. You get a fairly high hydrogen density in the storage of liquid, and that's really one of the main drivers for mobility applications located liquid hydrogen. You have the potential to go slightly higher with cryocompressed, but there's less demonstrations that have been done on that. So there's a potential there, but right now liquid hydrogen, in terms of a lot of data and a lot of demonstration, is the highest density storage and at low pressure. The last factor I want to bring up here, because it's very important when you're talking about aviation or any mobile application, is the mass fraction. So that's the mass of the hydrogen divided by that same mass of hydrogen plus the mass of the structure that's containing it. So you can think of it as how much of the mass of your container, storage container, is actual hydrogen versus the other structural materials that are present in the system. You can get up to 80%. Actually, in some of the single wall ones I'm going to show you, it's actually above 90%, but that's not practical for aviation applications. But this is much higher than most of the other formulations. So this is why there's an interest in a lot of mobility sector applications to get the performance required in terms of payload, speed, range, and those kind of parameters to go to a liquid hydrogen solution. So just a little quick history here. This is a great paper by Ray Radabaugh, who retired from NBS. Now it's called NIST. He did a nice historical paper in 2007 on cryogenics in general, but I wanted to point out hydrogen first being liquefied in 1898 by Sir James Dewar, which of course was then the name of double wall containment systems for hydrogen called Dewars are named after him. But the large scale production of liquid hydrogen didn't begin until the early 50s, 1952. And that was done at the National Bureau of Standards where Ray worked. And I think he may have been there at that time. But they started liquefying 320 liters per hour. This is some of the equipment here on the right-hand side, the dewars and some of the control systems. This, of course, was the vacuum tube era of controls and electronics. So that tells you how long ago. And that production of liquid hydrogen has been continuous since that time frame. So a lot of people aren't aware of how long liquid hydrogen production has been in place, and actually the whole supply chain. And we'll talk a little bit about that. A little bit more about the evolution of hydrogen systems. Going all the way back to the 1930s with the development of jet engines, hydrogen was actually the fuel that was used initially for jet engines. It was easy to ignite, easy to throttle the engines and do various testing. Going all the way back to the 1930s, it has roots in aviation that a lot of people aren't familiar with. And I've got some links in here. If you get the PDF and click on them, you can read some of the articles about some of this historical information. In the 1950s, Pratt & Whitney developed a liquid hydrogen jet engine with a afterburner, and did a lot of ground testing with it successfully. Checked out very well. It was actually part of spy plane work at that time. It ended up being the airframer that was associated with the liquid hydrogen engine didn't do quite as well as the Lockheed Skunk Works folks. So that ended up becoming the first spy plane, and it was designed on hydrocarbon fuel rather than hydrogen. An interesting kind of a diversion, or we might have been in hydrogen for quite a while from back then. In 1955, the Department of Defense funded work at NASA to demonstrate liquid hydrogen on an aircraft. So a B-57 airplane was modified to hold liquid hydrogen in one wing tank on the right-hand wing shown here. I'm sorry, the plane's right wing on your left-hand side. Oh, that's the helium. Helium tank for pressurization on one wing. And then the fuel tank, what's shown here is the fuel tank here at the bottom right of that figure. And there's a heat exchanger that would warm up the liquid hydrogen before putting it into the jet engine. And I should point out this jet engine was not modified. It was an engine that was used at that time with the conventional fuel that was used, which I think was diesel-based. So they would take off with engines in regular diesel and then switch over to hydrogen and perform various tests. And they did over a dozen of these flight tests. Very successful. The pilots were pleasantly surprised by how easy it was not only to switch back and forth between the fuels, but how well hydrogen performed in terms of throttling the engine, controlling the aircraft. They did a bunch of tests with dumping it and venting it and seeing what they could do in flight. Everything worked very well. There's actually a link to the report on this, as well as a YouTube that kind of shows some of the video of this plane in flight, which is kind of interesting. So from the 1950s, when that was done, until recently, aviation kind of didn't do much more with hydrogen. It made the jump, though, in '66 over to the Centaur upper stage, and that's what this picture on the right-hand side is. That was an upper stage launch stage of a rocket that ended up is still in production and still on as an upper stage for multiple rockets, including the new Vulcan by ULA. Liquid hydrogen fuel and liquid oxygen is the oxidizer, and that first had its first maiden flight in 1966. And now kind of moving along, there's a lot on this slide, but I'll just move through it quickly. So in the 60s and then through the 70s, the Apollo era, both of the upper stages in the Saturn rocket used hydrogen as a fuel. So the first stage was kerosene, but the next two stages were hydrogen. So the middle top here shows the hydrogen storage. It's the largest portion of the storage of that upper stage tank. Oxygen was then stored with a common bulkhead. This is done fairly often in rockets, liquid propulsion rockets, where they have a common bulkhead between them that's insulated. So liquid oxygen at the bottom, and then the engine, at the very bottom of the stack for that upper stage. And both of these two upper stages I mentioned was hydrogen. Also on board the Apollo, if you look at the bottom towards the left-hand side, was a fuel cell system using hydrogen and oxygen. It was alkaline based, and it provided all of the power, heat, and water for the astronauts throughout the entire Apollo mission. Once it was in low Earth orbit, all the way to the moon and all the way back. So if you remember the Apollo 13 incident, one of the reasons that was so dire of a situation when they lost their oxygen tank is that that fuel cell was providing all of those functions for life support: water, heat, and power. So very, very important, critical part of those Apollo missions. Moving to the shuttle era, right next to that fuel cell is now in the middle bottom is is a picture of the fuel cell system used on the shuttle. Now, this fuel cell system was used to provide all the power to the shuttle orbiter from after liftoff all the way through the mission to touchdown. Also hydrogen, oxygen based. And then the vehicle itself, the large orange tank that are very familiar to folks, that was about 2/3 liquid hydrogen. So if you look at the cutaway of that here on the far right, about 2/3 of that tank, the lower 2/3 or so, was liquid hydrogen, liquid oxygen at the top. And that fed the main engines of the orbiter that are kind of hard to see the flames because, of course, it burns very, very cleanly and almost invisible. And then there were solid rocket boosters on the side, but the main propulsion system was liquid hydrogen. So that takes up to about 2011 when the shuttle was retired. And now kind of bringing it into modern times, there's a number of rocket systems that are in current use and filled that gap between shuttle being retired and now, and are going forward with liquid hydrogen systems. So what I like to point out when I go through this is that we've got 60 years of demonstration, not demonstration, but operational systems, all the way life cycle from production of hydrogen, liquefaction, loading of the vehicle, consumption in the vehicle, fuel cells for power and heat. In the case of space systems, propulsion is primarily what liquid hydrogen is used for on the vehicle itself, all the way up until now and going forward. So the U.S.'s new space launch system, shown on the left here, and the new storage tank, which is now the new largest one. The other largest one was also at Kennedy, but this one's 50% larger, and I'll chat a little bit about that in one of the slides. But in addition to the U.S., European Union has been operating the Ariane 5 and now the Ariane 6. Liquid hydrogen is the fuel for that rocket for decades, a couple decades at least. Japan's rocket is liquid hydrogen. China's Long March rockets, several of their versions are liquid hydrogen. And India launched the, shown here in the middle top, their lunar lander, uncrewed, about a year ago, I think it has been now, launched on a liquid hydrogen rocket. So liquid hydrogen is the highest performance fuel, which is why it's used for so many of these, for these rocket systems. And Blue Origin, I'll mention also, is one of the two lunar lander companies that NASA has contracted to develop lunar landing systems, and it is using liquid hydrogen for its lunar lander. So with that, let me jump quickly into what's kind of been developed over the years to support all of this infrastructure in the space side, and where it has application in other industry and sectors. Vacuum jacketed liquid hydrogen dewars are pretty much the most common storage methodology from ground systems at laboratory scale all the way up to the largest ones that are currently in use. So these are double wall dewars. The space between the two walls is evacuated, so you've got a very hard vacuum. And then it's filled with various types of insulations depending on the use case. So what you get is a low heat leak from the environment. Because of that cold temperature of liquid hydrogen, of course, you need to minimize that heat load that's coming in from the environment. So that's what these double wall jacketed dewars are. They're often, as I mentioned before, named after Sir James Dewar, is how they're often stored, or almost exclusively stored, actually, with a few rare cases, and I'll show you those in a moment. The result is you've got very high thermal performance. For example, 0.5% per day for moderate to large size tanks, much lower for the largest ones. But I'll mention that you can reduce and completely eliminate that boil off by a variety of methods, and I will talk about that in one of the slides briefly. Operating temperatures pressures are low, usually below 5 bar. Again, you're operating at that very low temperature, minus almost 253 degrees C. So heat load is very important. And these tanks are generally, all the ones I've ever seen, are ASME code designed, tested, and stamped, at least in the US. And here's some examples on the left-hand side, some photos. The top and bottom are actual tanks, of course. A fairly large one on the bottom, that's at our facility at Plumbrook in Ohio. And in the middle is a schematic of some of the common components that you see in these Dewar tanks, from the double walls to the insulation, pressurization systems, drainage, that sort of thing. Now, the other types of tank, liquid hydrogen tanks that have been well studied, demonstrated, operational, and so forth, are single wall tanks that are used in rocket systems or launch vehicles. These are generally insulated with foam, and that's the way it was done with the space shuttle as well as the new space launch system. That foam insulation for that particular application with a rocket gives you just enough thermal resistance to prevent condensation of air constituents like oxygen onto the outside of the tank, and also tends to mitigate frost buildup on that external surface. So, and that's about all it does. I shouldn't say that's all it does, but the boil off is quite high though. So, and that's what that next bullet down mentions. The trade-off is, which is very important for rockets, of course, is you have much lower weight because you only have a single wall. It's a very thin wall. In some rockets, like that Centaur upper stage I mentioned, it's actually pressure stabilized, which even allows you to get much thinner. However, you've got that high boil off. So it's a good design choice for launch vehicles, so-called load and go type of a concept of operation, where you're loading quickly, you're topping it off, and then you have high consumption rate throughout the mission. Unless you're operating in that mode, these single wall tanks aren't going to be workable in most cases. They are also low pressure, 2 to 4 bar. One point to mention is these are not typically ASME designed, although there has been at least one case where they did a demonstration years ago where we did it to ASME standards just to show that you could launch a tank that heavy, and for cost benefit. Because one of the things you have to do with these very lightweight designs is do a significant amount of analysis and proof testing, since you're not following codes, they give you standard factors of safety that are typically very high. So you have to spend a lot of time and resources to prove out these designs, and then do a burst test as well. Here's a few pictures just to give you kind of a sense of the scale. On the left-hand side is the liquid hydrogen tank for the new SLS rocket. On the right-hand side is the liquid oxygen tank that is integrated on top of it. Again, these are single-wall tanks, both aluminum 2219, which is a suitable alloy for liquid hydrogen service, along with 300 series stainless, which are sometimes used, but not in these rockets. These are aluminum alloys. And here's a photograph of it integrated together. So you've got the liquid hydrogen at the, that lower portion taking up most of the volume, liquid oxygen at the top, very similar to where the shuttle kind of stacked it up. And then the engines at the bottom, and you can see the foam on the outside providing that insulation. This is an integration, and I show it not just for interest for folks that are curious about how these rockets are integrated, and this, of course, being the most recent and currently operational rocket at NASA now, the SLS. But I think it also gives a little bit of insight into some of the packaging you're starting to see in aviation, and why physics and thermodynamics drives you to certain commonalities. And one of them is this overall form factor of a cylindrical tank with domed ends. So this is the hydrogen tank here. And then the oxygen tank at the top. And if you break it down a little further, these tanks are made from rings that are welded together to provide the overall tank. Now, again, these are single wall tanks. In a double wall tank, you would have another a wall that would be similarly shaped, but then have the appropriate interconnects between fluid connections and structural supports to hold that outer wall in place, or the inner wall relative to the outer wall. But for this rocket, it's all single wall. And again, on the right-hand side is sort of an integration. And again, I show this just for maybe some insights in terms of what's been done for so many years, decades in the space industry in terms of integration and the kinds of similar problems that are going to occur, or not occur, but have to be addressed, I guess, or similar challenges when you try to integrate a liquid hydrogen tank into any kind of vehicle. I'll mention quickly composite liquid hydrogen tanks, because there's a lot of work going on in that now. NASA has looked at many types and designs over the years. I'm calling it mixed success. There was good things that went well and some other things that were challenges that are still being looked at. Here's a few of them. You've got kind of a stochastic structural failure. This material, composite materials don't yield and then rupture the same way that metallics do, or metal alloys do. They tend to more stochastically, or statistically, if you want to think about it that way, fail, where there's, you might bring test 10 to proof pressure, and one of them might go and the other 9 are fine. This is not uncommon. It's just it's a different type of stress that you get in those tank walls when you've got fibers inside of a composite matrix. They feel differently than metals. Also, permeability of hydrogen is one of the big things when you look at the chemistries for these composites. And a big one is interface connections. It's often overlooked. It's great to be able to make a tank out of a composite, but then you've got to be able to interface your supports to that tank, piping, and so forth. And then, of course, it's got to be able to handle the cryogenic temperatures as well as hydrogen compatibility. Metal inner liners have been used to improve a number of these challenges up here, including permeability. It can help with the piping connections if you're connecting to the metal part of the inner liner. You do have to be concerned, though, about CT, that's a coefficient of thermal expansion mismatch. So you've got a composite and you got some type of metal liner. They're going to expand and contract differently as the temperatures go up and down. So you've got to take that into account. But you do get some load sharing with those metal liners, which is also helpful. A couple of other things, fabrication layup defects and minor damage during processing of these tanks are a lot harder to detect than they are in metal tanks. A lot of times with metal tanks, you can detect visually a defect either in the manufacture or the processing. Not so easy a lot of times with composite tanks. So you have to have other ways of doing non-destructive evaluation, for example, to look at your various steps before the tanks go into service. But as I mentioned, there's a lot of development going on by a lot of companies in this area. Airbus, I think, has been probably one of the ones in NLR in Europe have been very publicly showing some of the work they're doing with this. In the U.S., Gloyer Taylor Labs has demonstrated some single and double wall composite tanks. So just a few examples of some of the work that's going on in the commercial sector now there. So let me sum up this, and I won't go over all of this, but I wanted to provide it in the stack because I think this is where the forward work and the forward challenges are going to be. When you look at ground versus rocket flight test tanks, there's a lot of information around those and a lot is known about them. But then when you compare them to what kind of new tanks are going to be necessary for, let's say, aviation applications, since that's the topic of this webinar, there's a lot of unknowns that are still being worked out, and they're going to provide a competitive advantage for those who can figure out the best approach. So I talked about the stationary tanks again. These are the type of materials, the type of insulation that's common. ASME, at least in the United States, code has been followed, and they've been certified by that. Very high factors of safety, relatively speaking, 3.5 or more. The maximum fill level usually is about 90% for these tanks, so you don't go much beyond that because you have to have some amount of vapor space because of the pressure buildup that can occur as heat comes in. Now for launch vehicles, I mentioned the single wall. We already walked through that. Much lower factors of safety. Typically, they're trying to get down to mass, of course, for those rocket systems. Maximum fill levels of 95% or even higher have been done and are operational. Again, they're trying to maximize the amount of fuel and minimize the mass of these systems, which is so critically important for launch vehicles and spacecraft. Now, when you start to move into aircraft, there's some open questions, right? You've got vacuum jacket and metal construction is probably going to be typical in the near term, but ongoing development of other types of materials, as we talked about, composite, but also thermoplastic designs are being looked at. Insulation that's consistent with the application, probably going to be a lot of multi-layer insulation, and I have a slide about that coming up. And a lot of custom designs, which brings to question what's the certification constraints or certification requirements that are going to be met, what safety factor, what maximum fill level. I think these are a lot of questions that are being answered probably in most cases in a proprietary manner by the companies that are developing these tanks. But over time, there's going to be some standardization that's going to probably going to have to occur in the aviation industry. A little bit on hydrogen safety. It's hard to go through talk about hydrogen without talking about safety, because there's so many misperceptions for one thing, but it is an important topic nonetheless. The three kind of mantras that I always like to think about, if you look at that fire triangle on the left-hand side, you want to prevent leaks, you want to provide ventilation, and you want to eliminate ignition sources. And that's the way you break that fire triangle by these three methods. Just comparing hydrogen and natural gas, I think, starts to give people a little better feel for what they're dealing with. It has a much higher heating value per unit mass than natural gas, so more energy per unit mass. However, since the density is much lower, for the same volume, we actually have less density in a hydrogen tank, regardless of whether you're comparing gas to gas or liquid hydrogen or liquid natural gas. You actually have less energy in the same volume because the density is lower for hydrogen. So one point that a lot of people don't think about in terms of safety, you actually have less energy in that same volume. Auto ignition temperature is actually slightly higher for hydrogen, so it takes a little more ignition energy. The flammability range is what most people tend to look at, and particularly people who aren't used to or haven't used a lot of hydrogen systems get a little nervous when they see this large range of, this is in air, 4.1% up to 74% is flammable. And it is something to be cognizant of and to design and operate with that in mind. However, if you look at natural gas at the lower end, 5.3, it's not that much higher. And from a practical standpoint, in terms of safety, you're always trying to stay well below that lower flammability range. So in many aspects, you're not dealing with that much different in terms of trying to diffuse or how much diffusion you want to get in air of any potential leaks that you have in your system. Now, hydrogen is a smaller molecule, so it's a little harder to design systems that will operate with a minimum amount of leakage compared to natural gas. But all of this has been tackled and is well known in the industry. Diffusion coefficient, much higher diffusion coefficient in air for hydrogen and natural gas. Again, this actually helps safety because it diffuses faster when it does escape. Neither of them are toxic to humans, and in fact, hydrogen is used as a deep diving breathing gas in some special applications. So there's no toxicity to it, but it is an asphyxiant. So if the hydrogen displaces enough air in an enclosed container, you could have an asphyxiation issue. Of course, it has to be contained because otherwise the hydrogen is going to escape very quickly because of the low density. Now, when you get to liquid hydrogen, we still have those three mantras I mentioned over here in the top left. But now, because of the liquid hydrogen state, there's a few more things that come into play other than just the hydrogen properties we already just mentioned. And this is just showing the temperature range, how low or where hydrogen fits when you liquefy it. It's somewhat warmer than helium is the only other gas that liquefies at a colder temperature than hydrogen, but it's much more colder than liquid nitrogen, liquid oxygen. When you get into that cryogenic range, you've got to think about first physiological effects in terms of humans might be in contact with with any cold surfaces that are holding the hydrogen or transporting it or transferring it. And then as well as material compatibility and that expansion and contraction that we briefly talked about, making sure you've got compatible materials that can expand and contract as needed with that temperature. The other part of the lower temperature with liquid hydrogen you have to always be cognizant of is the phase change from liquid to vapor, because any amount of heat coming into that stored liquid hydrogen that vaporizes represents a very large increase now in the volume. So, going from liquid to vapor, you have a pressure increase immediately. So you've got to look at overpressure, structural failures, pressure relief devices, that sort of thing. I mentioned a few codes down here. Again, it depends very much on where you're operating and where you're putting the system in place, which of these you follow. In the US, NFPA is the first place to go for the fundamental hydrogen code, which points to a lot of these other ones. ISO in Europe and other regions have their own codes and standards that need to be followed. It really depends up to your authority having jurisdiction which ones you need to follow. But I threw a few in here just to give some examples, as well as some supplemental material that's available out there. This is way too much to read through, so I'll just highlight. This is some liquid hydrogen safety considerations, the issue on the left-hand side, and then some example mitigations. This isn't following any particular codes or standards, but just general hydrogen safety. And you can see some of those things we talked about previously that come into play, physiological in terms of frostbite and asphyxiation, as well as sensory. Hydrogen is colorless, it's odorless. There is no odorant that's added to hydrogen like there is with natural gas, so you don't have an opportunity to smell any kind of leakage. And it's largely invisible flame in daylight. So if you do have a flame, you have to have IR detection or fire detection if you want to detect flames, or if you have a flare stack and you want to confirm that it's operating. At night, it's actually a light blue faint color, so it's not an issue at night, but at daytime, it's largely invisible. Materials and construction, of course, compatibility. I mentioned the overpressure, burst, rupture, very important. Any trapped volumes in your liquid hydrogen system, not just the storage tank, but piping that was going to have liquid hydrogen where there's the potential for valves to be closed at either end of the pipe that would trap a liquid hydrogen, that must have pressure relief in it so that you don't overpressure that section. Ice buildup and air condensation can occur if you have cold surfaces at the liquid hydrogen temperature or getting towards that temperature. Flammability, ignition, we talked about. One thing to remember with liquid hydrogen is if you do have a catastrophic rupture, let's say of a liquid hydrogen storage tank, it's going to hit the ground and boil off very quickly and rise. But for some period of time, that cold vapor is actually going to be heavier than air. So you can have a cold vapor cloud until it warms. So that's something that if you're looking at worst case scenario kind of things, you want to keep in mind. Contamination is always important with working with hydrogen in any phase, but certainly in liquid hydrogen. And I'll just mention this last one. In my experience, the lack of planning is what comes back to bite projects in many cases. And it's all those mitigations that I show here, basically thinking very carefully through every piece of your design, your operations, your emergency response, safe shutdown modes, all of those kinds of things, having good, not just design reviews, but safety reviews, and how you mitigate your safety concerns. Is there backup to that and so forth? So that's just a quick, I guess, check sheet, if you will, to think through as you're looking at hydrogen safety for liquid hydrogen. A few more safe hydrogen things. I'll just mention the things on the right-hand side and then point out what some of the photos are. Material selection I talked about, compatibility, vacuum jacketed, not just dewars and containment, but piping and valves are very common with liquid hydrogen systems. Almost exclusively vacuum jacketed piping is used. Sometimes valves you can get away with not vacuum jacketed depending on where they're used and if in the system, if the hydrogen is warmed up enough. Compatible sensors, you can't just throw regular sensors into these systems. They have to be compatible for cryogenic temperature and hydrogen. I have a link there to, I think, one of the companies that's been around for a long time doing that, Lakeshore Cryonics, I think it's the full name. Safe operation also includes having the capability for delivery and storage, of course, the system procedures, checkout. The use of, as I mentioned, reviews as well as check sheets. Cold shock and leak testing is very important. Liquid nitrogen cold shocks are very commonly used. That's what this top right picture is here. This is a liquid nitrogen shock test. I'm sorry, liquid nitrogen testing called cold shocking with liquid nitrogen, where you first operate with liquid nitrogen. It also allows you to actually go through various system operations before you get to hydrogen, so you can make sure things are working the way you think it will. But after this cold shock, then any leaks, you do some leak detection, and any leaks are tight. Flanges are tightened down where any leaks are detected, or other places. And then that cold shock can be done more than multiple times until you're convinced you've caught all your leaks basically in the systems that potentially could happen at cryogenic temperature. The control system pressure, we mentioned that phase change, very important. The heat coming in is going to vaporize. You've got to be able to control that pressure or relieve it if necessary in a situation where that is needed. And then you need to pressurize it, oftentimes to transfer. So even with a pump, you usually need some head pressure, or I'm sorry, a net positive suction pressure on your pump. Hydrogen is most often gaseous hydrogen used. I think in most cases, we used a lot of helium over the years in space industry, but that's become expensive and less available for commercial use. Thermal management is what's really important. When you think about the temperature difference between cryogenic hydrogen and ambient temperatures, it's a very large temperature difference. So you've got to manage that. And thermodynamics is in the driver's seat. That's what's going to drive your system, and understanding those thermodynamic conditions and how it affects is very important. So some of these other pictures, truck delivery, of course, is the way it's been done for many, many decades. There's been some train delivery over the years in the space industry, and barge delivery, I think, is still done at Stennis Space Center down in Mississippi because of their closeness to the coast down there. But truck delivery is by far the most common. Liquid hydrogen storage is shown here, the next picture down on the left, with a vaporizer that's used to provide pressurization to the tank when the transfer is needed. It takes off some of the liquid pressure of the tank, and then that's used for transfer. That's also commonly used in these truck deliveries when they load up or offload the truck into the storage tank. A couple of tanks we used for transfers, testing at NASA over the years. Another liquid hydrogen tank there. This is a composite helium pressurant tank, as a matter of fact, that was used in space flight. And then this is a cutaway view of vacuum jacketed piping. So I showed vacuum jacketed or dewars in a previous one. This is what piping looks like. You've got standoffs between the inner and outer pipe, but the same sort of general construction. I evacuated it with a hard vacuum between the two pipes, generally insulated, so that when you're flowing liquid hydrogen, and expansion joints to handle the warming and cooling of this pipe as it's being used. Yeah, I think that was all I was going to mention on this one. In terms of design, this is my taxonomy that I use for cryogenic thermal design. There's others that you'll find, but in general, you want to move from top to bottom in your design to get to a point where you've mitigated hydrogen losses or completely eliminated them, preferably. The first category I call passive. It takes into account everything from structure, how you're holding your how are the tanks basically structurally connected or structurally supported, as well as joints and materials and so forth. Insulation, we talked about some of the different insulation. And then in cryogenics, penetrations refers to anything that comes from a warmer temperature, like ambient temperature, and comes all the way into contact with the liquid hydrogen wall that's at a cold temperature. So that essentially is a heat leak path or a heat load into the tank. So always pay very close attention to those. And those are everything from piping for fill and drain, ports, wires, gauges, and so forth. You want to minimize them. And then when you do have to use them, you want to use very thin walls so that you have a conduction path that is gives you a high thermal resistance, essentially. The next category down I call hybrid, because it's a little bit between the passive, which doesn't use any electrical energy it's a passive thermal design, to some that might use some valves, valve actuation power. Joule-Thomson is one of those. There's a Joule-Thomson effect at cryogenic temperatures, where hydrogen is actually a cooling effect. At room temperature, it's warming, but there's a Joule-Thomson coefficient that at those temperatures, lower temperatures in cryogenic, it's actually cooling. So you can take a slug of liquid hydrogen, run it through a valve or other Joule-Thomson device. The pressure drop then ends up with a cooling of the stream, and you get a two-phase flow at the other end that's colder that you can use for various cooling methods in a heat exchanger that's either internal or external to the tank. Destratification is a method where when you have a tank that's being stored and it has colder fluid at the bottom, you mix it up and get that colder fluid towards the interface, and that'll pull the pressure down in the tank. And then boundary temperatures are very important. So you can do all kinds of I don't call them tricks, but design methods, I guess, to make it so that your liquid hydrogen tank is radiatively seeing something at a colder temperature. So it might be another cryogen, a warmer temperature cryogen if you're using one, like liquid oxygen, or it could be various shielding that you use that are cooled by your vapor flow, let's say to your fuel cell or something. And then the last category where you're using more significant power is active cooling. So you've got cryo-refrigeration, cryo-coolers, and potentially densification, although that hasn't been used to my knowledge outside of the space industry. I think we're getting close on time in terms of leaving time for Q&A, so I'll cover these last few kind of quickly. I mentioned the insulation types. Here's some photos of them. Everything that's reflective is multi-layer insulation, so it's usually aluminized mylar on both sides, and then Dacron netting in the middle to kind of keep them thermally separated so you don't have a thermal short. And then, of course, in a vacuum, that ends up giving you something that approaches a radiative set of radiation shields, thermal radiation shields that cut down the conduction. There's also foam in this picture on the left-hand side and far left, aerogel blanket, a different type of MLI where it uses, this was a company that developed it where it's, I believe it's thermoplastic standoffs rather than Dacron netting. Some perlite at the upper right has been around for a long time and used for a lot of ground systems. Some more pictures. The ones that look kind of smoky and translucent here are aerogels, pure aerogels. This is an aerogel blanket. And then microsphere glass beads or bubbles, which are used in the new largest liquid hydrogen container at Kennedy Space Center for insulation, which are better performing than perlite. This is some data that was recently collected for MLI. I like to point this out because MLI performs, is degraded by seams and penetrations that go through it. So you have to be careful about using any values that you see for MLI that was taken on a calorimeter, for example, because that does not include a lot of these degradation effects. So this set of series, and I just kind of want to highlight what they found, just as one major takeaway, is about 1 watt per meter squared, whether you're at liquid hydrogen or liquid nitrogen temperature or anywhere between, for about 30 layers of MLI, which is about 1 inch thick, is a pretty good first order rule of thumb for what kind of heat leak or heat load you're going to get through an MLI system in a vacuum. So if you've got a vacuum jack in a tank. I can't go over all these for time reasons, but you can go back and look at these. These are methods to utilize or mitigate your boil-off gas. Of course, you can feed it to a fuel cell for auxiliary power, which is a great way to use it. In spacecraft, we often use it for propulsion, for attitude control, either combusted or expanded through a nozzle. Not probably a lot of uses for that in aviation. Mixing, I mentioned already, you can destratify and lower that tank pressure so you can delay the time it takes for the pressure to get up to. And if you, depending on your concept of operations, you might be able to delay it long enough you don't ever have to vent or otherwise reduce that pressure. Vapor-cooled shielding, which I mentioned briefly, where you've got some of your vapor goes around, let's say, a tube on the outer part of the tank, so that when you're using it in a fuel cell, you're also cooling down the insulation and intercepting some of that heat load coming in from the environment. Thermodynamic vent systems we mentioned briefly already, and zero boil-off systems use those cryo-refrigeration systems or cryo-coolers to basically eliminate whatever's left. So you can get into a long-term zero boil-off system or state where liquid hydrogen can be indefinitely stored without without venting, I should say. as long as you provide the power to the cryo-refrigeration system. And of course, you can also re-liquefy with those systems. Any gas, if you do, let's say, a fill and you've got some vapor that's been generated during fill, you can re-liquefy them. And there's companies that have been doing work in this area and have products out there now available, like Gen H2. And then combinations of these, depending on your system. This is that new tank I mentioned during construction. You can see a little bit more about how that has that double wall construction. It supports the inner heat exchangers are what's providing that zero boil off. They have the ability to be connected to a reverse Brayton cryo-refrigeration cycle, which provides cooling. NASA Kennedy did a techno-economic study on this before we were brought in to do this design that showed that the electricity cost was pennies on a dollar compared to how much they were boiling off and venting when they didn't have zero boil off. So that was the rationale for designing the system for this. And this is now an operational system, the heat exchangers inside the tank. And that can provide zero boil off. It can also thermodynamically condition or cool the liquid inside the tank. And so this is a picture of it all now. The new tank here, that first launch of that system was in November 16, 2022, where they went around the moon uncrewed and came back and splashed down a very successful mission. And I think I'll end with this chart, which was my last chart, and just say this is a mnemonic that I came up with to help people think about the key characteristics of liquid hydrogen. And then maybe this could be a jumping off point for some of the questions as well. The mnemonic 2020 vision to the countdown to hydrogen. First 20 is the meters per second rise rate of gaseous hydrogen in air at ambient temperature. Very, very fast. So you just got to make sure you've got a way for the hydrogen to get up and out, and it will by buoyancy effects. 20K is liquid hydrogen temperature at 1 bar. And then the countdown starts with 5 safety tips that I mentioned earlier. 4 is the volume times of the amount of volume that's required liquid hydrogen versus common fuels for the same energy content. But you got to remember efficiency. If you're using a fuel cell, much more efficient, of course. However, there's 3 times the amount of energy in terms of the mass. And that's what this chart on the right shows. Is horizontal is energy per unit mass, vertical is per unit volume. So you've got to remember this when you're designing your system in terms of, those are the trade-offs you're making with using liquid hydrogen. 2 spin states, ortho and para. I'll just mention that para, it's very important to know this when you're working with properties for liquid hydrogen, which is 100% or close to 100% para hydrogen, whereas at warm temperature, it's about 75% ambient temperature, 75% ortho. So you got to know that when you're looking at properties. 1 proton per atom, of course, 2 atoms per molecule, and 0 carbon emissions, which we all know. But as beyond that, also no smoke, soot, or particulates. So sometimes people overlook that. Those are also very big impacts in terms of human health and public health for the use of hydrocarbon and fossil fuels. So with that, I hope I didn't talk too quickly, but I'll stop and take any questions that people may have. Let me get the.
Hi, Matt. Thanks so much. That was an amazing presentation. Per usual, I always enjoy listening to you present. I learn so much every single time. I'll start off with just a couple quick questions, and then after me, Tom, who's also one of our previous speakers on HYSKY Monthly. Tom, you can ask your question. So I was hoping you could.
Before you go on, Danielle, do you want me to stop sharing, or do you want me to leave this up?
I would leave it up. People will probably have questions about it. In fact, I think one of my questions does mention it. First, I was hoping you could just talk briefly about what Moran Innovation does and what sort of things you help people with, what your ideal client is, to whatever you're able to talk about. I know you're bound by some contracts. And then the second part is, have you or Moran Innovation developed any tools to help with these, the modeling and the analysis of using liquid hydrogen?
Okay, yeah, thanks for those questions. I pretty much all do consulting work now as a subject matter expert with liquid hydrogen. My contracts are split between NASA. Have been for the last several years on the human landing systems, both the SpaceX and the Blue Origin team's development. Of course, there's a firewall there; they're competitors. So, but I've been, in fact, I just recently ended after several years my support for the SpaceX, just doing Blue Origin now. But so that's a big piece of my consulting. I'm also do consulting with, I think you're familiar with Mark Herbush and NeoX with drones, hydrogen drones. And I've got a current contract that includes them as well, actually, with hydrogen microgrid storage for the Department of Defense in Pearl Harbor, Hickam joint base. So those are my current, and they're keeping me more busy than I would like to be honest. But that's an example, I guess, of some of the projects I'm involved in. So, but liquid hydrogen is where I've really gotten highly focused. As far as analytical stuff, I do have on my website, in my training page, a publication where I go through how to do some simple first order calculations with liquid hydrogen. Anybody can access that. There's no cost to it. I've also done some open source stuff with Python that's available, and that's also a link on my training page for that. I haven't spent as much time on it as I would like to in the last few months, but it may be a good starting point for some folks to look at if you're working in Python for some of your analytical stuff, to look at that and build off of it. It's open source, so you're free to take it and use it based on the license for that open source license.
I love it. When we'll do a write-up on this webinar and send it out to everybody. We'll include those links. By the way, just for the audience, Matt has a wealth of resources for free on his website. I think Rishav put the link in there earlier. Maybe Rishav, you could share it again.
You know, I did kind of put a barcode on the first slide of my deck, and I kind of covered up yours. Sorry, I put a barcode
No worries.
on my website, so that
Okay,
way.
great.
Yeah.
I thought that was our barcode. So okay, cool.
Yeah,
So you'll also be able to scan that.
Yeah, because I realized yours was to register, so I thought afterwards that doesn't really help anybody. So I thought,
yeah, that's perfect. Yeah, I love it. Okay, great. All right, the last piece of my question, and this is gonna be it. And then I'll let Tom go. For onboard storage in aviation, say, I don't know, 10,000 feet, when you had the boil off slide with different mitigation methods, which one, and I probably know the answer, it's probably it depends, but if you just, where would you start first if you were looking at onboard storage in aviation at about 10,000 feet? Which one of those mitigation methods would you look at first for being a potential solution on your boil off slide?
Well, beyond the passive stuff, of course, which is all designed for.
Can you, sorry to interrupt, but can you go back to that slide?
Oh, sure.
Where the first two you said they don't really, I can't remember. I think the third one was mixing.
Yeah.
This one, yeah.
Up there. Yeah. So, you know, I definitely would use all the passive techniques, of course, in your design. And then probably, you know, if you're 10,000 feet, let's say you're feeding, I'm going to assume it's a fuel cell power propulsion system. I think that's what most aircraft are looking at now, although it could be a jet engine as well, which I know, you know, Airbus and others are looking at. The first thing I would look at is when you're feeding you've got to warm up that gaseous stream anyway to put it into your fuel cell. So why not use that cooling that you have from your vapor and use it to either wrap around your tank or to wrap around key penetrations that are driving heat load into your tank. And there's other things you can do too, but you basically want to, from a system standpoint, maximize your heat exchange so that you're not losing or wasting that cooling capacity of your vapor stream. And then if you can get that vapor stream pretty close to what your inlet fuel cell requirement is, and you've done it by, you know, reducing your heat load to your tank, you're in great shape. And in some cases, that's might be enough to keep your pressure increase low enough in your storage tank with whatever your consumption rate is during flight. That's all you need to do. I think I know there are some companies that are looking at onboard active cooling, but I think it's going to be probably a less typical case for that to justify the power and the mass to have that on, unless you have very long periods of dormancy, which is going to be unusual, I think, and it would probably be on the ground before takeoff. where you might want to have some sort of active refrigeration. It might not have to be necessarily on the aircraft. It might be part of your ground support system. So those are two things that come to my mind, I guess. Danielle, is that kind of where you were going with it? Okay.
100%. You answered my question. Thanks. I think that was very helpful for many people on this call as well as me. Okay, Tom, you're up. Feel free to turn on your camera and unmute.
All right. Okay, here I am. Anyway, something that's out of curiosity because of some past experience of mine, and that was specifically in the area of the composite tanks. Are there being, given the experience so far with composite tanks, are there been any preferred construction techniques or composite materials for building tanks specifically for, let's say, liquid hydrogen, and anything in terms of pressure limitations that have come across that really give people in the composite area, a little bit to think about?
Great question. A lot of that work is proprietary, of course, right now. The ones I mentioned, Airbus and NLR, I think is it's a Dutch company, are doing research in that area. But the one company that I think has gotten pretty far with it is GTL, Gloyer Taylor Labs. You might take a look at their website. They've done both single and dual wall, and of course, they're to your question or point, their exact material makeup is proprietary. So I'm not sure how much they'll share of that, but you might get a sense of how they're pulling these things together. There's still challenges ahead. It's some of the ones I put in that last slide. I actually made that slide probably a couple of years ago, and I think some of those challenges still remain. I know they just recently announced that same company, GTL, they finished I think it was an SBIR for NASA, where they showed a composite pipe that can cool down very quickly. And I'm sure part of the attractiveness of that too is it potentially could be interfaced then with a complete composite tank. So I think those challenges still remain. I think, if I look at what Airbus has publicly said, they seem to be taking a two-step approach, or where they're developing metal tank first for the initial implementation, and then continuing to develop composites in parallel for later designs. And that to me seems to be probably a more what's the right word? Risk management of having that available when you need it, because I think the composite tanks still have a ways to go for a lot of applications.
Okay. Thank you very much. Great presentation. A lot of food for thought.
Thank you.
Yeah, and just to let you all know as well, Matt has taught the hydrogen aviation course with me at Flying High last year. Unfortunately, he won't be at Flying High this year.
Sorry.
But he is teaching the course with AIAA. I think 4 hours of just on this topic. So you'll get a much deeper dive. I highly encourage you all to sign up for that course. Rishav, maybe you could put that link in the chat again. Next up is Shaikh. I hope I'm saying your name correctly. And then Anurag, I think you're up after Shaikh. I might have those backwards, but let's start with Shaikh and then we'll do Anurag. Sorry if I'm mispronouncing your names. Just go ahead and unmute and you can turn your camera on.
Right. Yeah. My question is, the aerogels, are they also used for liquid hydrogen storage?
There's been, yes, work going on in that area for a while. Kennedy Space Center actually patented some formulations that they did with aerogel storage of hydrogen. I think both cold vapor and I think they tested with liquid nitrogen. And there were some companies that were trying to take that further with liquid hydrogen. None of it is publicly available, unfortunately, the work that companies have been doing with the liquid hydrogen with aerogels, but there's certainly some promise there, and as well as not necessarily just silica aerogels, which are the most common, but other material formulations. I know at the NASA Center, where I spent most of my career, they had developed polyimide aerogels, which have a lot of the same characteristics in terms of the very large amount of air and the ability to absorb, but they're a lot more robust. They don't crack and aren't as brittle as silica aerogels. But I think a lot of that, and I also actually just saw another news article about, I'm trying to remember, I think it was a university that had come up with another material, and it sounded to me like it had similar properties where it was nanoscale volume, in aggregate, large amounts of nanoscale volumes that were available within the matrix of the material that allowed it to absorb a lot of hydrogen. I think the key with a lot of these is going to be, though, besides the robustness, is how much energy does it take to get that hydrogen back out again, and in what form? Because generally you have to add heat to get it back out. So if you have heat available, whether it's part of your process heat or otherwise, then maybe it makes some sense. But I think there's a lot of questions still to be answered there, and a lot of it I think is being done behind the curtain of proprietary nature right now.
Right. Thank you.
Thanks for the question. Anurag, are you on the call still? If you are, you could ask your question.
Hi, Matt.
Hello.
Thanks for an excellent presentation.
Thank you.
And my question actually is an extension to Tom's. He's asked for on composites, and I basically want to extend them to thermoplastics, particularly those that are used on missiles.
Okay. Yes, I know there's work that's been going on in thermoplastics, but I know less about that. I'm not familiar or haven't worked with any of the organizations that have been doing that work, but I think, it has a lot of the same potential benefits, of course, with lighter weight and probably reduction of cost potentially, I would imagine, with thermoplastics. But I'm not familiar with which ones are going to be compatible with both temperature and hydrogen compatibility, though I apologize if that's not an area I've done a lot of digging into.
Okay. Anywhere where you can suggest we can have a look at to understand more on this, or?
Not off the top of my head. Let me think about that, and I can provide something to the HYSKY folks that they could, I'm sure, relay. But yeah, I have not been involved in any thermoplastic work, and I'm not familiar with any organizations off the top of my head that are looking at that. I'm just aware that I've seen the news feeds just like everybody else that comes through occasionally.
I could speak to that a little bit. My previous employer, who is a supplier to Boeing, they're doing a lot of research in that area. You can, I subscribe, I was a stress engineer in a past life. And so I used to get Composites World, I think is the name of the magazine. And they always do a piece on aerospace. It's composites and everything, but they have very up-to-date articles on thermoplastics. So I don't, if you look at their website, there's a huge conference. I'm totally spacing on the name, but I'll try to think of it during the next question. On composites every year. I think it's in LA or Anaheim, and they cover loads of aerospace and defense thermoplastics and things like that. So you might be able to learn some more from those. I've attended a couple of times, and that was probably 5 to 8 years ago. So I couldn't tell you exactly where they're at, but they were somewhat far along, but I think still in the testing phases. The last time I looked, I don't think anybody's actually using it commercially yet. I could be wrong.
Well, thanks a lot. That's good.
Thank you for the question. Next is Simon. And David, I do see your hand up. I'll try to get to you. I want to get to the ones in the chat first. Simon, you're up. Simon, we'll get to you next if you're still on. Daniel, if you want to unmute and ask your question, go for it.
Sure. Hi, Matt. Yeah, thanks for the presentation. I had a question on more on the liquefier side. How do you see the liquefaction to support the aviation sector? Do you think it'll be more like liquefiers, small scale liquefiers located at airports, or large centralized liquefiers getting better, efficiency and then transporting them?
Fantastic question, and one that I think is kind of being competed right now by various parties. Of course, the big companies, Linde and Air Liquide and Air Products, are building out as fast as they can their current capabilities. But I think it's going to be a little bit of all the above that you mentioned, to be honest. I think on-site liquefaction makes a lot of sense for larger airports, particularly ones that aren't close enough to make it economically viable to be taking truckloads of it, at a constant rate. And I also think that onboard one of the companies I'm working with, I mentioned earlier, Neox Systems, has developed a liquefier that liquefies on demand right in the tank of the drone. So this is public knowledge on their site. And I think that those kinds of approaches are going to be of interest too. It's part of the ground support system. So when the drone goes away, it doesn't take the weight of the cryo cooler with it, but it basically allows you to not have to worry about transportation or storage of the liquid hydrogen at all until you're ready to put it onto the vehicle and you actually produce it in the vehicle tank. So I think scaling that up might also be of interest for some applications as well. And it's kind of hard to see at this point which of those are going to pencil out. And I have a feeling it's going to depend a lot on the specific airport, what aircraft is being serviced and so forth.
Okay. Yeah. Thank you.
Yeah.
Thank you for the question. Peter Connors, you're up. And then after Peter, we will do David.
Well, Danielle, thanks very much. That's really not a question, but a comment. And, I've been following this area for a long time. And about 2.5 years ago, I participated by Zoom in one of the Energy Committee hearings at the Senate. That was a Joe Manchin committee hearing. And they were talking about the infrastructure for hydrogen and what has to be done. And I can tell you, I was just so impressed to see Senator Kelly, the astronaut, speak to the audience. That, gee, I'm the only person here that's ever actually used a fuel cell. And he went on to, talk about the benefits of hydrogen. So it's good to have guys like that with hands-on experience.
Yeah, that's true. He's kind of a rare bird, I guess, in politics that has that kind of background. Yeah.
And more generally, I really enjoyed your presentation. I know I'm going to have to listen to it 3 or 4 times, but there's a lot of impactful information.
Thank you.
And my last point is, I was at Wallops a couple of weeks ago, where they test the satellites.
Yes.
Track the satellites. My son-in-law designed one of the tracking systems.
Oh, cool. Yeah.
Very good.
Yeah. Very good.
All right. Nice to meet you.
Very cool. Thanks, Peter. Good to see you. Okay, David, I got to you.
Thank you. Hi, Matt.
Hi,
Thank you so
David.
much.
I saw your name come up when you were getting up. Good to see you again.
Yeah, good to see you too. So my question is on hydrogen and propulsion in particular. Many people are talking about using hydrogen in form of hydrogen fuel cells. And when it comes to aircraft propulsion, I feel like that is very much limited to the same thing that we have with normal propeller aeroplanes. So if we wanted to fly faster, is there any possibility of using hydrogen combustion such that it can act like conventional jet fuel?
Yes, and in fact, that's what Airbus and some of the other larger aircraft companies that are less public about some of their plans, although some of them, Rolls-Royce has done liquid hydrogen jet engine testing. DLR has also. So yeah, there's a lot of companies that are looking exactly at what you're describing, David, as a hydrogen fueled jet engine where you're not altitude restricted because of the air density and need to use propellers with fuel cells. So there's a bit of both. I think that the jet engines and the aircraft that they have to go on is a lot longer design cycle and a lot longer certification. So I think they're going to be down the road timeline wise. But as I mentioned in the history of it, I mean, there's already been a liquid hydrogen jet engine with afterburner developed in the 1950s. So there's not any real technical hurdles that are insurmountable there. It's just the integration of it into an overall aircraft and packaging everything properly for the fuel and the fuel delivery and so forth.
Okay, awesome. Thank you.
Yeah.
Great question. All right, this will be the last question. Albert, you're up. Keep in mind it's 11:59. We want to be respectful of Matt's time and everybody attending, so make it quick.
Very quick. It's related to solid state storage. And Matt, you said 2% or so, but you mentioned a few other technologies. What's the limit? Because I remember when I looked at the thermodynamics way back, I figured solid storage is dead. And to my surprise is I was at a recent meeting where people were looking at a large facility considering different way to store hydrogen, and they still stuck in solid storage, which it seems to me was kind of like a distraction. Any thoughts on that?
No, other than to commiserate with you or at least empathize with your position, I agree. I never thought there was. It seemed like with metal hydrides and so forth, there's use cases where those make sense, where you've got process heat that you can get the hydrogen back out, and you don't care about mass. But yeah, it seems like the latest solid state interest is in some of these aerogel type matrix materials where you have some 95% or 99% or whatever it is volume fraction that's available to absorb or adsorb the hydrogen into it. Having said that, I share your, I won't call it skepticism, I just haven't seen data yet that shows that it can store as much as they theoretically think it can, and then can be extracted economically to a reasonable amount afterwards. And again, maybe that's because a lot of it is still proprietary, the people that are testing it, but that seems to be what's driving a lot of the interest. I know, Danielle, you've looked at some of this as well. Maybe you have a different perspective.
Yeah, well, it's pretty much what you said. I was just going to say about 2 years ago, maybe even 3, there's a national lab. I think it's part of Sandia Labs out in California. I'm totally spacing on the name of it. But they do loads of research in hydrides, just solid state hydrogen storage in general. And we had them on. It wasn't NREL. It's not a very well known one. It's like a subsidiary of one of the labs. I'll find it. They developed a great chart for us. They presented for an hour and a half. The takeaway is it's very much still in the research phases, and it's not. At least about 3 years ago, it wasn't anywhere near being commercially viable yet. But I still can't comprehend how it would store more hydrogen. I struggle with that. Seems very counterintuitive. But with that, I just want to thank you again, Matt. It's been an honor. Thank you so much. We always enjoy doing work with you. Yeah, this will be available on YouTube. We'll send out an email. Thanks everybody for attending. Have an amazing week, and I'll see you in 2 weeks in Las Vegas. Not you, Matt, but I'll see you in 5 weeks. Thanks everybody. Have a good week.